Training large neural networks to convergence may be very difficult at times, and that is why between some hidden layers we include normalization, such that the mean of the layer outputs equals 0 and the standard deviation equal 1. To do this, we have, for example, this x, which is a layer output, which now becomes itself minus the mean value divided by the standard deviation. Now, the way we calculate the mean and the standard deviation actually depends on the normalization technique we're using. Many normalization techniques exist. We're going to treat three, which are the batch normalization, layer normalization, and instance normalization. Let's suppose we have as input data this image right here. Obviously, the image has a height and a width dimension, but then for every pixel we have in this frame right here, there are actually 3 channels. That's a red, green, and blue. So if we pick one pixel that's in this frame, if we pick up one pixel, that pixel will be represented by 3 values: the red, the green, and the blue. And that's why we could, instead of writing this 2-dimensional image, we could have it as this 3D figure, which in fact is a 3-dimensional tensor. So we have dimension by size, by height, by width, by channel number. If we suppose that the batch size equals 4, we have 1, 2, 3, 4 batches. Then for each of these, we have the height, width, channel, height, width, channel, height, width, channel, and height, width, channel. You may have noticed that instead of just 3 channels as we had in the input image, now here we actually have 5 channels. Now the choice of 5 channels is arbitrary and not really linked to this image here, as we could have any given number of channels depending on how our neural network is configured. And talking about neural networks, we would have this kind of hidden layer output mostly when we're dealing with convolutional neural networks, which we shall see subsequently. For now, we just suppose that we have this output where the number of channels 5. Notice that it's different from this input. The input is kind of fixed, where if we have a color image, the number of channels is fixed to 3. But in between the layers, the hidden layers, we could have many more channels. So we could have 10, 16, 24, any number of channels depending on how we configure our neural network. And in this case, we've chosen 5 channels. Notice how each channel has a specific color. Then we rewrite this formula here, which is x equals x minus the mean divided by the standard deviation. We do some recalls. The mean is defined such that it equals the sum of each value times its probability of occurrence, which is equals the value times 1 divided by n. In the case where all the different values have the same probability of occurrence, it means in this case, since we have n values, each value will have 1 on n probability of occurrence. Hence, the sum of all this 1 on n's will give us 1. We could take a simple example. So we suppose that we have, for example, 3 values, a, b, and c. Now, if these values have equal probability of occurrence, then their sum, or the sum of this probability, should be equals 1. And so since we have 3 values, we're going to have 1/3 for a, 1/3 for b, and 1/3 for c. And here, since we have n, is 1 on n. Now, since we're going from x equals 1 to n, we could take out 1 on n since it doesn't depend on x. Take out 1 on n, we're left with the sum of x from x equals 1 to n. And this now becomes the formula for the mean when all the different values of x have equal probability of occurrence. And for the variance, which is the square of the standard deviation, here's the standard deviation. The variance is the standard deviation square, is equals the expectance of x minus expectance of x, all of this square. Notice the way this is written. So inside here we have x minus expectance of x, that's x minus mu, all that square. So this is the definition of the variance. Now we've looked at this definitions. Let's go ahead to apply this in batch normalization. Note that here we're dealing with batch normalization. Now for batch normalization, as the word goes, we are going to calculate or compute the mean for whole batches. So if we decide to work with batches of 4, like in this case, we are going to do this sum right here over all values in a given batch. But with the difference that we shall only pick values in a given channel. So we'll pick this, 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 and this. And that's why here you see we have the sum for all the batches, we sum through the heights, sum through the widths. So like if we pick this channel right here, we sum through the height, or we sum through, first of all we sum through the height and the width, and then we sum through all the batches. So we go from this, 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 and that. If we had 32 batches, we'll sum through all 32 batches. Now the sum of all the x values, or all the pixel values we have here, which depend on the batch, depend on the height, and depend on the width position. And then once we get this, we divide by n by h by w, that's the batch size, by the height, by the width. Notice how in batch normalization we are not summing through all the channels, we're just picking up one channel and then going through all the batches instead. And then we do for the variance, which is sigma square 1 on nhw. We repeat the sum, but now applying this formula right here. Now if we have the mean to be defined as this, as the mean of x, this because it's actually e of x. So if we have e of x equals the sum of x times 1 on n, then it means e of x minus mu square can be gotten by simply replacing this x by x minus mu square. And that's what's been done here. We have x minus mu square. And in this case, we have xnij minus mu c, all of that square. The c is because we have decided to work on a given channel. So we are going to do this for one channel. So we pick one channel, we do that. And then we pick another channel. Notice that we'll pick this yellow channel here, pick this channel, and then we repeat this step. And then we continue with all the different channels. So for each channel, we do this. We normalize all the values throughout the batch. Next channel, we normalize all values, and so on and so forth. So that's it for batch normalization, which is the most popular of all these normalization techniques. Our next normalization technique will be the layer normalization. In layer normalization, we don't actually go through all the batches. What we do now is we focus on one batch instead. So we focus on this, we do normalization, we focus on this, normalization, and so on and so forth. So here we have x, which becomes x minus mu n divided by sigma n. Notice how we have mu n instead of mu c previously. This mu n is to say for a given batch. So now we do normalization for each element or each part of the batch, because this is like a batch of 4 elements or 4 data points, and then we pick one of these batches. So here we have that, and then mu n similar to what we had here. Now instead of summing through the batches, that's this, now we instead sum through the channels. So we'll pick this. Since we're working with this, we sum all the values that we have here. We sum through the height, through the width, through the channels. So basically we sum all the values that we get here, and then we divide by h times c times, or h times w times c. That gives us our mean. Similarly, we have sigma square, which is similar to what we had seen here. We have xcij minus mu n, all of that square. Now let's take another example apart from working with image data on the layer normalization. And the reason why we're doing this is because this layer normalization is very popular in working with sequential data, unlike with image data, although it's also used in image data. So yeah, we suppose that we have this input sequence where we have I am feeling good tonight. Now, when dealing with sequence data, we generally have this kind of input which we convert to one-hot vectors. Now, the way we convert this into one-hot vectors is such that if we have a vocabulary size of say 2000, we would have a one-hot vector of dimension 2000. That's 2000 different positions. So for each of this, we have 2000 different positions. And now, given that this I belongs to that vocabulary, we're going to look for the position of I in the vocabulary. So in this case, for example, I is the second word in the vocabulary. If we suppose we're starting from 0, so we have 0, 1, 2. I is the second word in the vocabulary, and so all the values are zeros except for the second word. So that's why we have 1 year. Now, am is the first word in the vocabulary, so we put a 1 and the rest zeros. Feeling is some word, say the 23rd word in the vocabulary, so we cannot represent that. Good, the same. Tonight, say the 400th word in the vocabulary, and that's it. Now, once we get this, we have a tensor of dimension batch size by sequence length, because we have 1, 2, 3, 4, 5, by vocabulary size. And if our vocabulary size is say 20,000 and our sequence length is 5, we can have batch size by 5 by 20,000. That's how we represent this input right here, which could be passed into a neural network. Now let's consider 3 batches of this kind of input. First of all, let's suppose we have one batch. This one batch is a representation of this I am feeling good tonight. So here we have 1, 2, 3, 4, 5 of this. That's the sequence length S5. And then for each of this, we have an embedding dimension. Now the term embedding is new. It's different from the vocabulary size. But what you need to know is that the embedding dimension is generally smaller than the vocabulary size. And the reason why we prefer this to the vocabulary size is that the vocabulary size, or the working with the vocabulary or with a full vocabulary like this, is actually less efficient, because here we are having a very sparse metric which doesn't contain any information for most of the values in this metric, since we mostly have zeros. And so instead of working with B by S by V, we prefer to work with B by S by E. So each word in the vocabulary is represented by a vector which contains E positions. So this is one batch, that and it's actually this. Suppose that we have another batch which contains another word. Just like with this would be one word, this would be one image, this would be another image, this is another image, and this another image. So now we suppose now we have this sentence, this here is it. Another sentence could produce this, another one producing this. So here we have a batch size of 3. And applying this to the layer normalization is quite similar to what we had here. We, instead of going from C to C, I to H, J to W as we had here, now we're going from S to big S and then E to big E. So we summing through all the sequence, or was summing throughout the sequence length, and then we also summing throughout the embedding dimension. And so here we have similar to what we had here, and then we have XSE, and all of this divided by or multiplied by 1 on SE. Then we could get similarly the standard deviation, or rather the variance, by having the standard deviation square and applying the same formula we've been applying throughout. Note that to get this, or to get sigma here, we just simply need to find the square root of whatever value we get here. So to obtain sigma, we just need to find the square root of this. So once we have this, we actually have sigma already, because it's just left to find the square root. Now we've understood this, we've understood layer normalization, we could move on to instance normalization. For instance normalization, the normalization, just as the word goes, is based on an instance. So not only we are not going to do normalization throughout the whole batch, but we are not going to do normalization throughout the whole channel. And this means that normalization is done for each patch in the channel. So for this patch, we have to normalize its values by summing up all the values in this patch. This is actually mu nc. As you could see here, we don't sum throughout the whole or through the channels, because we're working with just one patch, just one instance here, just this one. For example, just this one, just this one, just that one, just that one. And so to compute or to normalize all the values, unlike previously, or unlike with the batch normalization, where we'll just take the mean for all this, and with the layer normalization, where we take the mean for all the values here, now with instance normalization, the mean is taken for only one patch. So that's why we have this formula, and then the standard deviation as usual, x minus mu square. And that's it for normalization, which is a very important technique which is used in speeding up training.